Good morning, everyone. Today we are going to see the Unit 5 in Engineering Physics. What is the Unit 5? We are going to read about the Introduction to Crystal Physics. So, why we need to study the crystal physics? Is there any importance to us or for this world? Because nowadays we are detecting the radiation from the galaxies, from the stars, from the neutron star. There are so many celestial objects, even reflected light from moon. We are detecting. We are just analyzing the light using the semiconducting material. Then, if you are if you want to study the microscopic object, like if you are taking the microscopic object electron behavior, the how the atoms are arranged inside the material, we are using the electromagnetic radiation. For generating that electromagnetic radiation, we are using the crystals. Or if you are taking that lasers, now the laser is one of the fundamental thing we are using. Our life as well as the laser are coupled both. So we can't separate these two as to individual part, because without laser we are not going to grow in the near future. We are not going to develop any instrument. So using the help of the laser, the we are doing everything now. Even a lot of industries are using the laser, even laser cutting technologies, even the minute cutting, even atomic level cutting, we are using the lasers. So for generating the laser, we are using that crystals. So it's important to study about the crystal physics. That's why we have an unit 5 as a crystal physics in engineering. This is your introductory level course. So you are going to just simply understand what is the crystal, what are the behavior of the crystals, what are the properties of the crystal through this chapter. So crystal physics is most interesting physics nowadays. Everyone is doing research in the crystal physics. They are using the simulation software, they are creating the crystals, they are just manufacturing, they are just doing the business with the crystals. Even in your future, if you are going to attend any interview in some company, definitely you will get some basic question in the crystal physics. So definitely this is one of the most interesting chapter, as well as this is one of the most fundamentally we got to understand the atomic behavior in the solids. So this is a one of the chapter will explain everything. You can understand about the microscopic world. Even if you want to understand the macroscopic world, we are using the detector, the semiconductor detector. So for understanding the world, the complete world, even whether it is microscopic or in macroscopic, because the macroscopic world, it is explained by classical physics. Even if you are starting from the most important topmost scientist, the Isaac Newton, he explained that using the new his equation, the macroscopic world, the attraction between the two objects. Even if you are moving into microscopic world, the Schrödinger quantum mechanics plays an important role. If you want to study both together, definitely you need the crystal. Without the crystal, you can't understand anything, even macroscopic world as well as the microscopic world. So for that, we have to study about the crystal physics. That's why we have an in engineering physics as one of the unit is a introduction to crystal physics. Let's we move into the crystal physics. We can start study the crystal physics. Before entering into the crystal physics, we can ask one question here. What is the crystal physics? This is the most important question in this topic before entering to the topic. So, if you want to answer this question, the crystal physics or the crystallographic physics is a branch of physics that deal with the study of all possible type of crystal structure by using X-rays or neutron beam or electron beam. The X-ray diffraction method reveals about the internal structure of the atom. it will tells us how many possible orientation of the planes inside the crystal, how many planes are arranged in which direction, the how many the number most number of planes inside the crystal. So it will reveals about the complete information about the crystal. That's why we are using the X-rays to study the internal structure of the crystal. The neutron beam diffraction also, it is similar method like electron diffractions, but we are not going to study in detail in this course. Just I want to give the flavor of the this kind of diffraction. The neutron diffractions also is similar to the X-rays diffraction. It will also the same purpose we are using to study the internal structure of the crystal, and beyond that, as well as the electron beam diffractions. If you are firing the using the electron beam, the diffraction pattern will change according to the behavior of the material, the internal arrangement of the atomic material. That's why we are using X-rays, neutron beam, the electron beam to study the crystal physics, because we can't directly focus the atomic structure, the crystal structure. Why? Because the atomic interplanar distance is 10 power minus 10 angstrom. It is that much order. So you can't take simply, you can't zoom that atom, you can't just see that atomic behavior. It's an angstrom level. So that's why we are using the electromagnetic radiation or the neutron beams or electron, the fundamental particle firing on the material, the crystal material, to get the information about the internal structure. That's why this field we can call it's a crystal physics or crystallography physics. Next question, why we have to study the crystal physics? That I already answered in the beginning part. So if you want to understand the physical properties of the crystalline solid, without the internal, the actual structure, we can't study the physical properties. Once if you know the physical properties, once if you want to know the physical properties, definitely you want to know the actual structure of the crystals. Without the actual structure, we don't know anything. That means we can't jump into inside exactly the crystalline solid. That's why we need this chapter. So in the next slides, what we are going to see, there are two most important useful of the crystalline solid. That is the thing we are going to see. The one is the source, how we are using the crystals as a source, that we are using the crystal as a source in the light emitting diode as well as the laser physics. We are using these crystals as a fundamental source for generating the light. That's why we are calling it a source. Then the next important thing, we are using as a detector. If you want to like study about your planet or something, the we are just how we are studying about the planets, other planets, how we are studying about the stellar system, even how we can study about the microscopic particle. We have to collect that electromagnetic radiation, the reflected light from the so many planets, the generated light from the stars or other stellar system. So or the interaction, after the interaction, the light is emitted from the atom. So we need to collect those light to study the internal structure of the all the object, whether it is microscopic or macroscopic. To study the structural behavior, we need to collect the light. For collecting light purpose, we are using the detectors, the crystals as a detectors. So that's why we need uh, to study the crystal structure. Without that, these two things impossible. So the next slide, we are going to study how the crystals are using as a source as well as the detector. Answer this question, why we need to study the crystal structure. Once if you know the crystal structure, then you can identify whether it is a direct band gap semiconductor or indirect band gap semiconductor. Here I thing you will study in detail, in depth about the band gaps of the semiconductor in the physics for electronic engineering or the electronic circuit analysis or some other topic. Here there are inside the crystal electronic energy level, only the two energy bands are allowed. Either electron is allowed in this energy state or the valence band, the lowest energy state. There is no allowed state in between these two energy. Here if you look at this y axis, this is the energy axis. So there is a bigger gap between these two energy level. This we can call the band gap. So if you are see the conduction band, the lower position, as well as the valence band, the highest position, the highest energy state, if you are aligning on the same line, x-axis here is a momentum axis. If it is aligning on the same momentum axis, we can call it a direct band gap semiconductor. These kind of semiconductor we are using to generate the light sources. So that is here, it is shown here. Already you have studied about these light sources in the laser physics, because the laser physics will tells us the homodyne as well as homojunction laser, heterojunction laser. Here this structure in general it is called the heterojunctions laser. Here actually this is called quantum well structure. Here what I want to tell, we are not going to deal this structure in depth. Here if you look at this structure, the aluminum gallium arsenide, this P, the P plus means highly concentrated hole gallium arsenide. There is an active region. Then the lower bottom is N-type aluminum gallium arsenide. The another lower bottom material N-type gallium arsenide substrate. N-type means it's a electron concentrated material. P-type means it's a whole concentrated material. So if you look at this material, gallium arsenide, aluminum gallium arsenide, these two kind of materials we are using to generate the light. These kind of material are semiconducting material. It is a crystal material. It is having some ordered arrangement of the atom inside the material. So we are choosing this kind of crystal material or crystal structure to generate the light source. If you look at this diagram, the red dot, it will emit the light. So the direct band gap semiconducting material, it's a crystal material we are using to generate the light sources in the laser sources. Even LED also we are using the semiconducting material. They are crystal structures, simply it's crystal structure, that's all. So without the knowledge of the crystal structure, how we can generate the light? That's why we need to study the crystal structure. The next one, the detector, that is the thing we are going to see. That is and also we are not going to see in depth. Just I want to give the flavors for why we need to study the crystal structure. Here it is shown here that left hand side diagram, if you look at this diagram, it is indirect band gap semiconductor material. Look at that, y-axis is the energy axis, x-axis is the momentum axis, k-axis. The top of the this is the allowed state, the bottom valence band, conduction band also allowed states for the electron inside the semiconducting material. If you look at that, these two, the topmost energy of the valence band, bottom lowest energy of the conduction band, they are not exactly at same k value, that means same momentum value. It just misaligned. That's why we are calling it indirect band gap semiconductor. So this kind of material we are using as a detector. So if you look at the simple diagram for the crystal the detectors, this is a schematic structure. Here the wave represents the photons falling on the crystal structure. Then there is an absorption of the photon. It will generate the electric signal in the outside the circuit. So according to the intensity of the light or frequency of the light, we will it will show the load resistance here, the voltage. According to that, though we can analyze the output voltage, we can uh, get the knowledge about that the incident wave, that the incident photon nature, whether what frequency it is falling, at what intensity it is falling, what is the power of the photon, everything we can study. For this purpose, we are using the crystal structure here, because the crystal structure is most important structure. Even the its atomic arrangement is so perfect, so it will reveal the at least the ideal information about the photon characteristics. So that's why we need to study the crystal structure, whether we are using as a source or whether we are using as the detectors. We have to know about the crystal structure inside, at what arrange, in what way the atoms are aligned, the what crystal structure it is. So we have to know everything about the crystal structure. We are ready to study about the crystal structure. Before entering into the that crystal structure, we need to study about the types of solid in general. In world, how many types of solids exist? One of the solid is a crystalline solid. So the first type, it is the crystalline solids. It is exists in the world. The next type of solid, it is exist, that is a non-crystalline solid, or we can call amorphous solid. So any solid, if you are taking in the world, you can categorize in these two categories. Suppose if you are taking like a gold, we are wearing the gold, like a gold watch or a gold chain or gold rings. So these are we can categorize as a crystalline solids. If we are studying about the non-crystalline solid, you can say the example like rubber or plastics. They are non-crystalline solids. So any material, if you are taking in the world, you can categorize in these two category. The category in the type of solid, that is a crystalline solid. What is a crystalline solid? That we can ask that question. So the crystalline solid is a solid material whose constitution particle are arranged in highly ordered manner. That means if you look at that atomic arrangement, it is perfectly ordered. That we can call those solid or in crystalline solid. So then it will form a crystal lattice that extends in all directions. So look at this diagram, right hand side diagram. This we can call it's a crystalline solids. If you look at the atomic arrangement, it is orderly, highly orderly arranged. If you look at the top array, it is linearly arranged. The bottom array, it is slightly displaced, but it is also highly really arranged. This is we can call the highly ordered manner. It is the atomic arrangement in the crystalline solid or in highly ordered manner. Next point we studied the crystal lattice that extend in all the direction. If you look at this direction, it will be yes, this extend in this direction. If you are look at this direction, suppose if you are considered this is a two-dimensional crystalline solid. If you are look at this direction, this is also having some directional point of view. See here, the atoms are arranged in this manner, but in this direction. If you look at the next array, it is also highly ordered, but in this y direction it is arranged in perfectly manner. That's why we can call this solid is a crystalline solid. And then they do have the directional property, so they are called as anisotropic substance. What do you mean by the anisotropy? So anisotropy means, if you are just to look at that, suppose say example, this crystalline solid we are using as a conductor for conducting property. If you are measuring the current in the x direction, in this direction, IC, that will be different. Suppose the conduction current IC in this direction, if you are measuring this same current. Suppose if you are measuring the current in this direction, that IC will be different. That means why x direction the conduction current is different from the y direction conduction current mean the atomic arrangement. If you look at the x direction, the atoms are touching together, definitely it will be highly conducting. But if you look at this y direction, the here one atom, suppose if the electron is try to move here, it will feel that the gap, then it will again. So there is a periodic gap it is facing, that which one means the electron. That's why the current, the conduction current, it will be different in the x direction as well as in the y direction. They are not equal. This kind of property we can call is anisotropic property. That's why we are calling this crystalline solid are anisotropic in nature. This is just for example I told, so don't consider this is an actual, just I want to clarify what is the anisotropic. That's why I took this the conduction current in this crystal as an example. So the last character, they have a narrow range of melting point. If you look at the crystal, the gold, the melting point, if you are just heat the gold above the like 1000 degree uh, centigrade, so it will melt the gold. Or if you are just if you are look at that like platinum, that melting point, it will be like 1768. Even if you are heating above 1700 degrees Celsius, the platinum title will melt. Lead, that if you are taking the lead, that melting point, it will be around like 320 degrees Celsius. If you are heating around 320 degrees Celsius, it will melt. If you take the hardest material, the tungsten filament or tungsten one, if you are heating above 300 and 3400 degrees Celsius only, it will try to melt. So they have definite melting point, very rare narrow range, not wide range. Wide range means suppose that material will melt if you are giving 100 degree or 1000 degree in between any range, that is a wide range. But the crystalline solid, they do have the narrow range of melting point. These are the some important characteristics of the crystalline solid. Next type of solid is non-crystalline solid or amorphous solid. So what is an amorphous solid or non-crystalline solid means? They do not have the perfect crystalline order. Usually these materials are condensed phase material. That means there is no orderly arrangement of the atom. Everything is condensed. So they do not possess the long range translational order or periodicity. So if you look at this diagram, the amorphous diagram, look at the atomic arrangement. If you're taking this atom, the next atom is aligned slightly down, the next atom is slightly up, the next is slightly down. But the arrangement of down up, it is not in periodic manner. If you are look this atom, it is arranged in the topmost position. If you look at this atom, there is no periodicity between the successive atoms. Even they do not have any translational symmetry. You can look at these gaps, they are bigger gaps. Here its gaps are more, here the gaps are less. So this kind of materials we can call the amorphous material. So what is the characteristics of the amorphous material? We can ask one question. They do not possess any characteristic like a crystalline solid. They do not have directional properties, and so they are called as isotropic substance. In crystalline solid, we can characterize that is a anisotropic substance. Anisotropic substance because the conductivity or the magnetization or the some other behavior in one direction, it is different from the other direction. But in amorphous solid, the atomic arrangement is not so perfect. So if you are giving the current in any direction, if you are giving in y direction or in x direction, the conductivity will be same, the conduction current will be same. Even if you are taking that amorphous solid, if you want to magnetize this anyway amorphous solid, we are not going to use as a magnetization purpose. I'm just saying, if you can magnetize the amorphous solid, the magnetization will be same in all direction. The amount of magnetic dipole arrangement in the x or in the other direction, the both are will be equal. So that's why we are calling that amorphous solids are isotropic substance. Then they have wide range of melting point. If you are melt that amorphous solid, you can't say exactly this is a melting point. Just we now said about in crystalline solid, the gold having melting point around 1060 degrees Celsius. We can't say the amorphous it's exactly that melting point. It is having wide range of melting point. It can vary like 100 to like 1000. So it can melt in, but I mean these two temperature, that's why we are having that wide range of melting point. But it will vary according to the wide range will vary the different type of, it's a type of amorphous solid, it will vary different types. So that we have to understand first. So for example, you can say that glass, platinum, rubber, these are the examples for the amorphous solid. But I didn't say the example for the crystalline solid, but I told the in melting point temperature, the gold, the platinum, the silver, the tungsten, these are the crystalline solid example. The crystalline solids are perfect conductor. Some of them are semiconductor. Even you can call the crystalline solid the semiconductor silicon, germanium, selenium. These are the selenium anyway we are not going to use most of the applications. The germanium, the silicon in the pure form it won't act as a conductor, in the impure form it will act as a conductor. That's why we are calling these two germanium as well as silicon we are calling semiconductor. Purest form it won't conduct, impurest form it will conduct. These are the good example for the crystalline solids. The example for the amorphous solid, that is I have given here. In this chapter, we are going to deal the crystalline solid. So we have to know its type. What are the types of crystalline solid? They are categorized into two types. The first one, that is single crystalline solids. The next one, that is polycrystalline solid. Now we are going to study what is a single crystalline solid, what is a polycrystalline solid. Just we are going to touch the topics. We are not going to in depth of the single crystalline as well as the polycrystalline. So first we can ask one question. What is a single crystalline solid? First category, then the crystalline solid is a single crystalline solid. So that is the thing we are going to discuss now. Look at the diagram. This is, we can call it is a single crystalline solid. What is a single crystalline solid? This is a material in which crystal lattice is continuous with no grain boundaries. Here I didn't say anything about the crystal lattice, but I will tell the crystal lattice. What do you mean by? Suppose if you take the simplest area, if you are taking this is a two-dimensional crystal lattice because only y-axis as well as the x-axis is here. Because here the atomic arrangement I have shown here in the two direction. That's why it is a two-dimensional crystal lattice. Here the smallest area of the crystal lattice, it's a that triangle. That is a, this is a area. So this we can call it's a crystal lattice or unit cell. What it will do, it will repeat. See here, here. Even you can compare with the bottom also. See here, the bottom, it is also triangle. See here, again you can couple. So the triangular shape, it's repeated in the x direction as well as the y directions. That's why we are calling it a single crystalline solid. Only the triangle shape is repeating. That's why it is called single. Single means only you can see that the triangle shape. It is orderly arranged. There is no grain boundaries. What do you mean by grain boundaries? Means you can't see any gap or you can't see any different structure here. If you're having two different structure in the crystal lattice, the gap between the two different structure we can call it's a grain boundaries. Maybe in the next slide you will get a clear idea about the grain boundaries. Now anyway we understood what is the crystalline solid. Category is a polycrystalline solid. Look at the diagram here. If you look at this diagram, here the crystal lattice is triangular lattice, but here it is also triangle. But if you look at these two, in between these two, there is a gap because the arrangement of the that shapes is different. Even you can categorize in this group of atom as a hexagonal structure also. See here, here it is hexagonal, here it is triangle. Here you can categorize this one as even if you are repeating this group of atoms, it is belongs to the hexagonal structure. This group of atom, it is belongs to the triangle structure. This group of atom, you can just draw the complete diagram. So it's belongs to this kind of structure. So you can categorize three different kind of structure in the single crystal. That's why it is called polycrystalline solids. So the most of the inorganic solids are polycrystalline, including all common metals, many ceramics, rocks, as well as the ice. Ice also good example for the polycrystalline solid. Which is, if you are asking, even if you are just keeping in your fridge, in the freezer, the normal ice, the water H2O, that ice also is a good example for the polycrystalline solid. Here, the either it's a single crystalline or polycrystalline, you can just tell it's a metallic or non-metallic kind of crystalline solids. The example for the metallic crystalline solids: copper, gold, aluminium, magnesium. The non-metallic crystalline example: carbon, silicons, germanium. So these are the two different types of the metallic, but it can be the single crystalline or polycrystalline. Anyway, that we are not going to discuss in depth. So now we understood some basic idea about the crystalline solid. What are the crystalline solid? What is its behavior? What are the properties of the crystalline solid? How many types of crystalline solid is exist in nature? Now we are now ready to just this is the introductory part. Now we are ready to move into exact the crystal physics, how you can define the crystals inside the material. That is the thing we are going to see now.